자, 우리가 지금 beam theory를 지금 하고 있습니다. And as announced last time, the chapter 11 and 12 have been rearranged. So we have a two parts. One is the beam theory, deflection due to bending. That is the second part. And the first part is the purely bending beam theory, where we start with the deflections and stress-strain relations and equilibrium. So which is very similar to a torsion theory. So I would like to review again this beam theory, which is again is very important, the most important topic in solid mechanics. This table summarizes the analogy between bar, shaft, and beam. I think this analogy is very useful for you to understand not only bar and shaft, but also understand the beam theory as well. I will go through this one, and then I will go back to deformation assumptions and so on. So for the beam case, where we consider uniform beam bending moment, okay, that's the force we are considering. Whereas in the shaft, we consider twisting moment, and that's the uniform twisting moment. And in the beam, we apply a uniform bending moment. So to create uniform bending moment is applied at the end. Then along the beam, the bending moment will remain constant. So as shown here, we apply a bending moment at the end, then to be in equilibrium. On the left-hand side, this also should be a bending moment to end, so that total beam will be in equilibrium. And then at arbitrary sections, there should be some internal any cross section, we will have another constant moment to have this, the part of this beam should be in equilibrium. So anyhow, once we apply the moment at the end, every cross section will have a same bending moment, where we same moment as a moment we apply. So that's the bending moment end. And for the cross-sectional property, in the shaft, the cross-sectional property was the polar moment of inertia, IP, and this was the result of the torsion theory. For the beam, similar to a polar moment of inertia, we now have a moment of inertia, which is defined as the y. Y is the height, coordinate height and scale, and dA. That is the cross-sectional property. And stress is the moment divided by I times y, and strain simply divided by E, And deformation, which is I think is the most important, is the theta, angle of rotation, where we apply the moment L divided by E, J, and material property is E. So understanding this beam, at the same time you pay attention to a shaft and bar, so you can understand all solid mechanics theory by using these analogies. So these analogies between those three structures are extremely important. Okay, so again, as I mentioned, I will start with beam deformations. How we get this one? Please just 1 second. I need to install some software. Please stay online. So that 3 plus 5 plus 1 flow chart will equally apply to this beam theory, torsion theory, and bar theory. But more importantly, all the theory start from deformation assumptions. Okay, the bottom part, the deformation assumptions that we need to keep in mind. Why we start with we have to start with a deformation theory? Well, the theory we are trying to develop is for the structural analysis. In other words, that is not 100% accuracy, but good enough, accurate enough. And that's why we need to start with deformation observations. So this flow chart, as I used last time, there is a bar and shaft and beam, and the force we apply, and bar and shaft beam, you can see the P and T and moments. That's the force we apply, and the equilibrium is that the moment we apply should be same as the resultant of the internal stress, sigma x times y dA, or torsion is the and that's the moment and the stress, they are all in equilibrium. And then this stress should be less than strength, and this stress and stiffness and Young's modulus. Now this Young's modulus, and then this strain, okay, strain needs to be determined from a displacement field. That is the, I think, the most important point. So in beam theory, the deformation relation is that epsilon x equal minus y over r. Y is the axis from the neutral axis, and 1 over r is the curvature, now which can be written as a d theta dx. That is the theta is the deformation, and epsilon x is the strain. So this is the most important point, and this is the where the theory starts. Sorry, we need to install the certain software. Please keep. Okay, so that again, let's go through one more time. The equation we are trying to drive is the again, epsilon x is the minus yr, and minus 1 over r is that d theta dx. This is the strain and deformation relations. And so let's try to obtain these relations. To do so, let's say we have a beam, and where we apply the bending moment at the end and moment to end. And let's start with the left-hand side is the clamp. Of course, there will be a reaction force and moment to end to be in equilibrium. And we want this is the theta equal 0 reference plane, and then it gradually increase the theta. What I mean by theta is the one, let's say each sections, this one, for example, will have a certain rotate. Originally was a vertical, but it has a slight rotation. That is the, this is the angle. And next one, we have another rotations, and that is this much angle, as you can see here. This one was the vertical, and that is the angle of rotation, and that is the angle of rotation. Same for here. So we do same thing, all cross sections, and finally at the end, we have a theta 0, and theta 0 is the one here, theta 0, and where we apply the moment. Okay, so here what we can obtain from this relation is that, say this arbitrarily, this is the theta. Okay, this is the a d theta. D theta means the over the dx. Okay, let's say this is the dx, and this is the from here. Okay, this is the d theta. Okay, d theta times r. R is the constant from here to there, which is the neutral axis. So r times d theta, this length, and which is assumed to be same as dx. Well, strictly speaking, this is not exactly same, but it's good enough. And the reason we can say so is that this axis as a neutral, is called a neutral axis, and this one is the this part. So this one we don't have any epsilon x. Epsilon x is this is the x. So x directionally there is no length increase or decrease. So we can say that d theta r is equal to dx. So from this, what we can have is that d theta dx is 1 over r. So this is the curvature, and this is the theta. Theta is the angle of rotation due to a moment we apply. So this is the one we obtain. And now, so this 1 over r is the dx d theta. But how about this one, where this relation epsilon x is minus y over r is in next, actually, these relations So say this part, pay attention to AB, and this is located and y equal y in arbitrary position relative to neutral axis. And this length, now let's take a look at this, the strain of this part. This is the before deformation, and this is the after deformations. Okay, after deformation, we have A prime and B prime. This is the Y. Now, by definition, the extractional strain is the after deformation. After deformation is A prime and B prime, and minus AB, which is the before deformation, divided by before deformation. So L prime minus L divided by L. L is the original length. L prime is the after deformation. And A prime, B prime, and this one, as we already mentioned, this is the curvature R, and this is the Y. So this coordinate, this curvature is from here to there, is the simply R minus Y, right? R minus Y. This is the radius of curvature. So R minus Y times B theta is this length of A prime and B prime. So R minus Y B theta is the A prime B prime. Now, how about the original length? Original length was this one, AB, and AB is the same as here, same as this one, so this length. But what is this length? Well, this length is nothing but this length, and this length, in terms of d theta, we simply multiply radius of curvature r times d theta. So the before deformation, the length of this one was this length, and that's why we can say r d theta, r d theta. So all terms disappear, and what is left is minus y, I'm sorry, only this one, minus y and r. Okay, so this is the A strain, and 1 over r was the, as we noticed previously, r d theta times dx. Okay, so the most important result is this epsilon x is the y minus y times dx d theta. Okay, that is the one we need to drive. Once we have that one, next step is pretty much straightforward. Since we have this epsilon x is the minus y times d theta dx, then again sigma x equal E times epsilon x. That is the stress-strain relations, and equilibrium is that we apply the moment, and internally, okay, if we at this part, we have a moment, and internally there will be a stress distributions like that. And this stress, simply by definitions, moment due to this stress distribution is that sigma x times, okay, sigma x times y. Sigma x times dA is what? That is the force, and y is the for moment, and we have a moment. Okay, that was the explained in here. So moment. This one, you can say that at the left-hand side, we have this one. Okay, so here and on the right-hand side here, it's the same thing. They have to be same. So here we just apply the moment, and moment is on the right-hand side or left-hand side, the same thing. So moment is simply sigma x times A is a force in this area, and you need to multiply y, then is the moment. So the moment is simply minus y times dx, sigma x, and actually sigma x has to be dA, right? dA, that is the moment. So sigma x we already have E times epsilon x, and epsilon x we already have a minus y times d theta dx. So we put it back to moment, and what we have finally, we have a sigma x minus moment I dz and y. Actually, from here, what was unknown, I will just you can easily flip back, and e times this is a minus, there is a minus, so that will be a plus, and e times and d theta dx is the now is a constant out of integration, and y squared dA, and this is the we simply call I, and what is unknown here is this one. So d theta dx, which was assumed at the very beginning. So this one is simply EI times moment. Okay, so this is the one, and d theta dx, we can say that theta 0 divided by L, and L can go there. So theta 0 is the moment, L divided by EI. That was the beam theory, and I highly recommend you to drive this equation several times so that you can feel very much confident about this derivation. It's so important. Now, what I'm trying to do here is that there is a analogies for the beam and beam or moment and cross-section property, and this is the theta, and now the sigma, once we have this is the dx, df, theta is known, next one is what? We can put this back to here. So put this back to here, and so we can say that this one is this dx, d theta dx, and we can get it back. Sigma x equal minus E and moment, and EI, as you can see here. So this is the disappear. But this is only when we have a constant material property. That constant material property, we have this sigma xx and this one. what if we have a we have a multiple layer, such as this part is the A material and B material and C material. What if we have several layer materials? Then the whole procedure is the same, but we have to pay attention to how we calculate the moment, how we calculate the sigma. That's what I'm trying to do now. But still, you need to keep that in mind. This is the backbone for the whole beam theory, for the section where we have which has the constant material property. Last week we had a homework that beams in series or parallel connections. So we have this case and that, and beam in parallel. We did several cases, but what I want to do now is that where we have the beam consists of, this is the, let's say, cross sections. We have different materials, okay? Different materials. Different materials. So let's say we have this is the B material. So different Young's modulus and EA, and this one is a and top and bottom we have a different another materials. Say Young's modulus EP, okay, and this one let's consider that this one is the HA, and this one let's call HB, and the bottom let's say same HB, and the point here is the layered beam, where we have a combined section which has the combination of materials. Well, the theory we're gonna drive can be easily applied to many multi-layer. So let's consider this 3-layer and also this HA and HB and HB. This is the kind of a special case, but the point is that we consider a layered beam. So this is the very important case for the beam theory. So first step, actually, we, again, as usual, the strain these relations. You remember that we have an equilibrium, we have a stress, equilibrium, and stress, and this is the stiffness, and this is the strain, and this is the displacement, right? We have a 5 flow chart, and now I'm trying to emphasize this part, and that was simply the theta dx was a moment, dx, the theta was the 1 over r, and epsilon x was minus y over r, right? And minus, put it here, y d theta dx. this is the strain displacement relations for a constant, the section with the constant material, right? All EA. I mean Young's modulus. But here, the point here is that if you look at this derivation or result, strain displacement relation, there is no terms related to material properties. In other words, these strain displacement relations will equally apply to here and apply to here. So this strain displacement relations has nothing to do with the number of layers. Okay, so which is very important. And again, deformation is always like deform at the, with respect to a left-hand side, always be deform like that, whether it has the one material or two material. Okay, so this one is important to understand. You may think that, oh, because of this two different material, this section may be like that, but that is not true. Okay, regardless of number of layers, or regardless of material property, the cross section is always cross section always remains plane and remains vertical with respect to this neutral axis. Okay, so plane remains plane and vertical. That we need to keep in mind. Okay, so this step is equally applied to any section. Now, second step. This is the first step. What was the second step? The second step is this one, and simply sigma x equal Young's modulus E times epsilon EX, which also apply to any material. But here we have to be we have to keep in mind that we have two different material, right? This is the A for the middle one, and so this is the A, and the top one we simply have a different stiffness relations. So our we don't need to write down here, but for the regions of for the A part is simply we say this one, and for the B part we simply say this one. Okay, so this is also nothing new, and this is the stress strain relations. Now, third part is the equilibrium, which is the here equilibrium. Equilibrium means that, well, we apply the moment here, we apply the moment, and this moment will cause a certain I will just write down the section, the show sections like that. We apply the moment here. Now the stress distributions, okay, stress distribution, whatever stress, the moment and stress, a relation will be simply a sigma x times dA is a force and times y. That's the definition of a moment. That is the moment equilibrium. So this is the has to be used in equilibrium, right? And now let's put it back here and here. Now sigma x, what is a sigma x? Well, Young's modulus E times the strain y, d theta dx and dA. But there is a y here. There is a y here. We have a y scale. Okay, up to here. we don't have any problem, and this whole procedure is the same as the case where we have only one material. Now, here, this, what does it mean, dA? dA and integration over the whole cross-section, right? Whole cross-section here, whole cross-section. So this is the whole cross-section. So when we integrate, we cannot integrate them easily, or just because this E is no longer constant, right? We have two different materials and depending on this region. So what we need to do is that simply divide E. But what we know is that before this, what we know is that this part, d theta dx, can be simply out of integration because this is nothing to do with cross sections. Okay, this is nothing to do with the cross section, and this can come out of integration. But again, when we integrate this part, we cannot take this E out of integration because this is the E is varying over the cross section. Okay, so let's say we can say E times y squared dA and d theta dx, but when we integrate them, we have to divide them into two parts. So E y squared dA and over A area and plus and E y squared dA and B area, and then dx d theta dx. Okay. Then this one in region A here, we now is a constant, and we can take out of the integration, and this E is we can also taken out of this integration, and then this should be EA, and then y squared dA integrated over A plus EB and integrations of B y squared dA. And then d theta dx. Okay, so this is the one I would like to emphasize. I will rewrite again here. The moment we apply will be simply EA. Now, what is this? This is the moment of inertia of the area A. And what is this? This is the moment of inertia for this area B. So EA, I will call IA plus EA, EP, and IB, and d theta dx. Okay, so you can say d theta dx is simply moment divided by EA, IA, EP, IB. If we have more than two, we have many different layers, we can simply, we can easily derive and the final equation will be integration of EI and II. Of course, the II is the moment of inertia, okay? And I equal 1 to n. Okay, that is the moment, and this was the unknown which we have to derive from moment equilibrium equations. And once we have this one, we can put it back to here. And once we have this one, we can calculate the sigma x and here. So imagine this one is a constant, and this is the y here and there. And if we draw the sigma x distributions, and here, now this EA and EB, they are different. So the moment distributions moment distribution and the stress distribution from this relation can be like that, and like that, and like that. So this is the stress distributions. One stress distributions. So here the point is that since this is the y, there is a linear, okay, linear. But since here is the we have a different Young's modulus, then here we have a different slope. Okay, different slope and different slope. So this is the again inside is a EA and outside is EB, and top and bottom is a symmetric, and this is the one we can obtain. Okay, so this is the stress distributions, and again the point is that we get this one d theta dx and put it here, and then we can get the stress distributions. So as you can see here, the moment theory and stress derivation for layered beam is exactly same as the one section with the one material, except that we use these two different definition of the Young's modulus. So when we integrate them, we need to be careful. Only one only difference is that we have to divide them into two parts, and then we have this. Now this one, IA and IB, is that IA is now the moment of inertia is the middle part, and IB is the moment of inertia of the top part. Right, because the IA is integrated only over A. A is this part, and that part, and this IB is this part. So IA is simply since you know this height, and you know this one, and you know this one, and you can have that. You can obtain that. And as long as you know this I, say this is a B and H, and this is a 12, H3 and B. That's the moment of inertia. And if there is an empty, you get the whole moment of inertia and minus this one. That's the way we can calculate. So if from this, if EA equal EB, then simply this equation will become the same as the beam theory for the one materials. Okay. Again, this is the beam theory. Beam theory for the layered beam. Layered beam, this is the again extremely important. There is the actually one subject which is the calculation of the determination of the neutral axis, which we already consider in this determination of a neutral axis. And again, we do exactly the same here. And sigma x is now you need to multiply E over Y over R, and you have two different material. And so for this case, since they are symmetric, the neutral axis will be the will pass through the centroid, but if for the arbitrary cross section, we have to redefine the neutral axis. But the way we determine the neutral axis will be the same as this one. Okay, the neutral axis should exist so that the total force over the cross section Fx should disappear, because simply we didn't apply any external force in x directional force. Okay, so that is the another point. Okay, so that I want to emphasize for the beam theory. And tomorrow, of course, we want to discuss together in class of the beam theory, and I would like to have your feedback or some questions on beam theory, multi-layered or single-layered, and any questions will be welcome. And then let's move to a beam theory, second part of a beam theory, which is the deflection due to bending. That is the last, very last core section in solid mechanics. Okay, thank you, and then see you tomorrow. Okay, bye.
Bye-bye.